We present the Relightables, the first system capable of reconstructing relightable volumetric videos of humans. Our reconstructions are built on highly accurate and detailed geometry. The normal map contains high-frequency geometric detail that would otherwise be difficult to recover. On top of this geometry, our system paints a high-resolution texture. Crucially, though, our reconstructions also include reflectance information. This allows the reconstructions to be relit in a new scene, so that their appearance can be made consistent with the lighting in that scene. The result is substantially more realistic than what would be obtained from a more typical volumetric video, where the lighting of the capture studio has been pre-baked into the texture map. To obtain this capability, we built our capture system through augmentation of a light stage. The light stage itself contains 331 programmable LEDs, capable of producing arbitrary lighting conditions at a high frame rate. Our capture system is attached to the light stage and consists of many units containing a high-resolution RGB camera, 2 high-resolution IR cameras, and a custom illuminator. In contrast to other illuminators, ours produces an extremely dense pattern, which is amenable to precise stereo matching. The light stage itself rapidly alternates between emitting 2 color gradient illumination patterns. This gradient information can later be used to infer the reflectance properties needed to perform relighting. Our volumetric pipeline processes each frame in parallel in the cloud and produces temporally consistent meshes. Reflectance maps necessary for accurate relighting are also computed. For more details, please see the paper. We now compare our method with the state-of-the-art. Notice how Colette et al. Tends to oversmooth the geometry, whereas Du et al. Struggles to reconstruct the entire performer. Further, although their method performs mesh alignment, it does not generate topologically consistent meshes. In contrast, we can generate high-quality reconstructions with topologically consistent meshes. We now demonstrate the importance of our texture alignment approach. Notice how without this alignment, the rendered results suffer from motion artifacts. In contrast, these artifacts are largely removed by this step. One of the contributions of our work is a principled method to choose precisely when a new triangulation should be employed, usually as a result of a topology change. In contrast, past work can struggle to perform the switch at the correct time, causing unrealistic deformations. Our relightable volumetric videos can be placed into arbitrary lighting environment maps. Crucially, the subject can be relit so that the reconstruction's appearance is consistent with the lighting conditions in the environment. When the lighting environment map is changed, the lighting of the character is adjusted automatically. Here we show more examples from our relightable performance capture system. We now demonstrate real-time renderings of our volumetric capture. Notice how these reconstructions can be smoothly rendered in standard graphics engines, such as Unity. Naturally, our reconstructions can also be placed into synthetic scenes. Here you can see the geometry of the synthetic scene casting shadows on the subject. Post-capture effects are also possible as demonstrated here. When the real-world lighting conditions can be inferred on a mobile phone, the reconstruction can be realistically placed into and relit in the real world. Thanks for watching.